Today, we're going to uncover this beautiful, hidden story behind a piece of math a lot of us probably had to memorize but never really, got. We're going to see how a confusing rule from algebra class is actually this brilliant piece of ancient geometry.
Remember this thing? Yeah, this is the rule for completing the square. It's a formula that was just drilled into our heads in school, right? A purely abstract set of symbols we had to use to solve equations.
But have you ever really stopped to wonder what it means? Like, what are we completing? And why a square? Well, that question is exactly what we're going to answer today.
So let's dive into this by framing it as an old mystery. We're going to travel back in time, way back, to an era before algebra was all about abstract symbols, when it was all about tangible shapes.
Okay, so this was the kind of problem that ancient mathematicians were trying to solve, not with x's and y's, but as a real-world puzzle that actually involved area. To them, this wasn't just some random equation. It was a physical statement. It described a real relationship between shapes and their areas.
So here's what this thing is actually saying. X squared is the area of a square with some unknown side x. 10x is the total area of 10 rectangles, and together, their total area has to be exactly 39.
So how in the world did they solve for that unknown side x? Well, they didn't use formulas. They built it. They solved the problem by literally drawing it out. And we're going to do the exact same thing right now. So this diagram here basically shows you the entire process. They started with that unknown square x squared right there in the middle. Then they did something really clever. They arranged those 10 rectangles around its sides. And this creates a bigger shape that's almost a perfect square. You can see it, right? The final step was to spot these little missing corners, those gaps that needed to be filled to truly complete the square.
So what's the area of those missing corners? Well, each one is a little 2.5 by 2.5 square, which means the total missing area is exactly 25. And this right here, this is the magic number. By adding this 25 to our original area of 39, we're about to create a new, perfectly completed square.
And here it is. Our brand new, large square has a total area of 64. Now think about it. If a square's area is 64, its side length has to be 8, right? And if you look at the diagram, that side is made up of our original x plus 2 of those 2.5 segments. So x plus 5 must equal 8. And that means our original unknown side, x, has to be 3. Just by rearranging some shapes and filling in the gaps, they solved the equation without needing any complicated formulas. Pretty amazing.
Okay, now for the big reveal. Let's connect this beautiful geometric process directly back to that abstract formula we were all forced to memorize.
This is where it all clicks. You remember the b over 2 from the formula? That wasn't just some abstract math, it was literally the act of splitting our rectangles. And b over 2 squared? That's the area of the corner pieces we just added to complete the square. It was a physical instruction the whole time.
So when we write this out in algebra, we're just describing the final picture. X squared plus 10x plus the 25 we added is equal to a perfect square with a side length of x plus 5. The geometry and the algebra are telling the exact same story. So why does any of this ancient stuff still matter today? You might be really surprised. This one simple geometric insight is the foundation for some of the most powerful tools in modern science and technology.
I mean, the influence of this method is just astounding. It's the very foundation of the quadratic formula. It's how we find the vertex of a parabola. And maybe the most surprising thing of all, it's a critical tool in modern artificial intelligence.
Yeah, really. When an AI learns, it's constantly trying to minimize its mistakes or its loss. Finding the absolute lowest point of that loss is essential. And the process for pinpointing that minimum value? It relies on the exact same geometric trick of completing the square that we just walked through.
You know, what this whole journey really shows us is something pretty profound about the nature of mathematics itself. We tend to think of it as this world of cold, abstract symbols, but that's not where it started at all.
At the end of the day, what this reveals is that algebra wasn't born from abstract symbols. It actually came from the physical, intuitive act of rearranging shapes to figure out unknown areas. It started as a visual, tangible way of thinking.
It really makes you wonder, doesn't it? If this much beauty and intuition was hiding behind something as simple as completing the square, what other profound secrets are still waiting to be discovered in the math we think we already know?